In this video, I will be doing a proof of the AC or product sum method of factoring a quadratic trinomial with a leading coefficient that is not equal to 1. I want to factor a quadratic trinomial written in standard form such that ax squared plus bx plus c equals ax plus h times x plus n, under the assumption that a, b, and c are all integers that do not collectively share a common factor. For example, let's say we want to factor this trinomial. Suppose we had two integers, k and h, such that their sum was equal to the first degree coefficient and their product is equal to the product between the second degree coefficient and the constant term. By some trivial trial and error, we can find that the values of h and k are 3 and 4. Now we split the first degree term of our first trinomial into two other terms with these new coefficients. Afterwards, we simply factor by grouping. Magic, right? But hold on a minute. Why exactly did we multiply these two terms? There has to be some mathematical reason for this other than it just makes sense. Well, this seemingly nonsensical multiplication actually does have a reason. I'll explain how. First, let's take that standard form quadratic again. Then let's multiply it by the first coefficient, a. Just like this, and next we're going to expand it. Now, while it doesn't seem immediately obvious, if we substitute a times x for something like, let's say, ax equals y, and we substitute that, we're going to get something that looks sort of like, and boom, we've made a breakthrough here. Now, why is this useful? Well, if you haven't noticed, this is a quadratic trinomial with a coefficient that is equal to 1, right here on this squared term. So, this is useful because, first of all, now we know where our strange, mysterious multiplication of AC comes from, right? So let's try to factor this now and see what we get out of it. So the general form of a factored trinomial, or a factored quadratic trinomial with a coefficient equal to 1, is something like x plus h times x plus k, right? So this happens to be equal to, when we expand it, it's something like x squared plus h plus k times x plus h times k. So we're going to apply this form to our quadratic right here. So how we're going to do that is we're just going to substitute b for h plus k and ac for hk. Now, it's important to keep in mind that since we substituted AC for HK, that means that AC equals HK. Now, this will be important later on. So now, let's factor this back into something like this, which will be easy. It'll just turn out to be something exactly like this. Now remember that y equals ax. So now that we have factored this quadratic, let's bring it a bit closer back to reality and substitute y for ax. Ax plus h times ax plus k. Now, if we expand this, we are going to get now, recall that we multiplied our standard form trinomial by the first coefficient a. So to clean things up a bit and make things a bit easier to work with, we are going to divide this by a, which will leave us with this. So at this point, we've split up that first degree coefficient into two separate terms, each with a different coefficient, and we have this interesting term here, which is hk over a, which, if you recall that ac equals hk, I did that backwards. If we divide both sides by a, that gives us c, which makes sense, right? This is just our standard form trinomial, just with the first degree term split up. Okay, so now that we have this, let's try to factor it. We are going to change this so that k is something a bit easier to work with, this k coefficient right here. So how we're going to do that is we are going to take our equation here from earlier, ac equals hk, and we are just going to solve for k, which leaves us with k equals ac over h. So now we're going to substitute ac over h for k right here. Now we have something like this, which now will make it easier for us to group terms together since we now have this a here. So let's go ahead and group these terms together and group these terms together and take out the common factors. So we've sorted out the common factors, which now leaves us with this. Now we've hit a little snag here in our factoring process, but it's actually really simple to fix. All we have to do is demonstrate that what's inside of this parentheses is the same as what's inside of this, which is actually really easy. All we have to do, x plus c over h equals x plus k over a. We're going to subtract off this x, which leaves us with c over h equals k over a. Now, while it's not immediately obvious, we can just cross multiply this and this, which will give us AC equals HK. This means that what's inside of this parentheses is equal to what's inside of this parentheses. So to demonstrate that a little better, we're going to say that a new variable, let's say n, let's ignore this here, n equals c over h, which means it also equals k over a. Alright? So we're basically just going to substitute n into our almost factored trinomial here, and we're going to finish things up. So we're on the last legs of this proof here. All we're going to do is we're going to substitute c over h and k over a for n, and we're going to finish factoring. So let's take this over here, ax over x plus n plus h times x plus n. Overlapping a bit there, but that's okay. So now we're just going to finish factoring, which leaves us with ax plus h times x plus n. Now, if you recall from closer to the beginning of this video, this is exactly what we're looking for. This is our factored trinomial.